Welcome to Huberman Lab Essentials, where we revisit past episodes for the most potent and actionable science-based tools for mental health, physical health, and performance. I'm Andrew Huberman, and I'm a professor of neurobiology and ophthalmology at Stanford School of Medicine. Today, we are going to discuss the science and practice of flexibility and stretching. The important thing that I'd like you to know is that flexibility and the process of stretching and getting more flexible involves three major components: neural, meaning of the nervous system; muscular, muscles; and connective tissue. Connective tissue is the stuff that surrounds the neural stuff and the muscular stuff, although it's all kind of weaved together and braided together in complicated ways. So here's a key thing that everyone should know, whether or not you're talking about flexibility or not. Your nervous system controls your muscles. It's what gets your muscles to contract. So within your spinal cord, you have a category of neurons, nerve cells, that are called motor neurons. Those neurons release a chemical. That chemical is called acetylcholine. The release of acetylcholine from these nerve cells, these neurons, onto the muscles causes the muscles to contract. And when muscles contract, they are able to move limbs by way of changing the length of the muscle, adjusting the function of connective tissue like tendons and ligaments. Now, within the muscles themselves, there are nerve connections. And these are nerve connections that arise from a different set of neurons in the spinal cord that we call sensory neurons. These spindle connections within the muscle that wrap around the muscle fibers sense the stretch of those muscle fibers. So now we have two parts to the system that I've described. You've got motor neurons that can cause muscles to contract and shorten, and we have these spindles within the muscles themselves that wrap around the muscle fibers, and that information is sent from the muscle back to the spinal cord. It's a form of sensing what's going on in the muscle. Now, why would that be useful? Well, what this does is it creates a situation where if a muscle is stretching too much because the range of motion of a limb is increased too much, then the muscle will contract to bring that limb range of motion into a safe range again. Okay, so just to clarify, this whole thing looks like a loop, and the essential components of the loop are motor neurons contract muscles, sensory neurons that we call spindles are sensing stretch within the muscles, and if a given muscle is elongating because of the increased range of motion of a limb, those sensory neurons send an electrical signal into the spinal cord such that there is an activation of the motor neuron, which by now should make perfect sense as to why that's useful. It then shortens up the muscle. It actually doesn't really shorten the muscle, but contracts the muscle that brings the limb back into a safe range of motion. So that's one basic mechanism that we want to hold in mind, this idea of a spindle that senses stretch and can activate contraction of the muscles and shorten the muscles. The next mechanism I want to describe, and once again, there are only two that you need to hold in mind for this episode, has to do with sensing loads. So at the end of each muscles, you have tendons, typically, and there are neurons that are closely associated with those tendons that are called Golgi tendon organs, right? These are neurons that are sensory neurons that sense how much load is on a given muscle, right? So if you're lifting up something very, very heavy, these neurons are going to fire, meaning they're going to send electrical activity into the spinal cord. And then those neurons have the ability to shut down, not activate, but shut down motor neurons and to prevent the contraction of a given muscle. So for instance, if you were to walk over and try and pick up a weight that is much too heavy for you, meaning you could not do it without injuring yourself. There are a number of reasons why you might not be able to lift it, but let's say you start to get it a little bit off the ground, or you start to get some force generated that would allow it to move. But the force that you're generating could potentially rip your muscles or your tendons off of the bone, right? That it could disrupt the joints, and it could tear ligaments. Well, you have a safety mechanism in place. It's these Golgi tendon organs, these GTOs as they're called, that get activated and shut down the motor neurons and make it impossible for those muscles to contract. There are also mechanisms that arrive to the neuromuscular system from higher up in the nervous system, from the brain. And those mechanisms involve a couple of different facets that are really interesting. and I think that we should all know about. In fact, today I'm going to teach you about a set of neurons that I'm guessing 99.9% of you have never heard of, including all you neuroscientists out there, if you're out there, and I know you're out there, that seem uniquely enriched in humans and probably perform essential roles in our ability to regulate our physiology and our emotional state. So within the brain, we have the ability to sense things in the external world, something we call exteroception, and we have the ability to sense things in our internal world, within our body, called interoception. Interoception can be the volume of food in your gut, whether or not you're experiencing any organ pain or discomfort, whether or not you feel good in your gut and in your organs. The main brain area that's associated with interpreting what's going on in our body is called the insula, I-N-S-U-L-A. It's a very interesting brain region. It's got two major parts. The front of it is mainly concerned with things like smell and to some extent vision, like if you smell something good to approach it or if you smell something bad to avoid it. The posterior insula, the back of the insula that is, has a very interesting and distinct set of functions. The posterior insula is mainly concerned with what's going on with your somatic experience. How do you feel internally? It mainly batches information into yum, I want to keep doing this or approach this thing, or continue down some path of movement or eating or staying in a temperature environment, etc. Or yuck, I need to get out of here. I don't want any more of this. I don't want to keep doing this. This is painful or aversive or stressful. In your posterior insula, you have a very interesting population of very large neurons. These are exceptionally large neurons called Van Economo neurons. Neurons that are, again, unbeknownst to most neuroscientists, and they seem uniquely enriched in humans. Why is that interesting? Well, these Van Economo neurons have the unique property of integrating our knowledge about our body movements, our sense of pain and discomfort, and can drive motivational processes that allow us to lean into discomfort and indeed to overcome any discomfort if we decide that the discomfort that we are experiencing is good for us or directed toward a specific goal. And then there's the other really interesting aspect of these Van Economo neurons, which is that these Van Economo neurons are connected to a number of different brain areas that can shift our internal state from one of so-called sympathetic activation. So this is a pattern of alertness and even stress, sometimes even panic, but typically alertness and stress, to one of so-called parasympathetic activation, to one of relaxation. Oftentimes you'll hear that stretching should be done by relaxing into the stretch. Well, what does it actually mean to relax into the stretch? Well, these Van Economo neurons sit at this junction where they're able to evaluate what's going on inside our body and allow us to access neural circuitries by which we can shift our relative level of alertness down a bit or our relative level of stress down a bit, and thereby to increase so-called parasympathetic activation and to literally override some of those spindle mechanisms, even the GTO mechanisms, but especially the spindle mechanisms at the neuromuscular and musculospinal junction. I'll give you a brief example of this that you've already done in your life and that we all have the capacity for. What I'm referring to is the monosynaptic stretch reflex. This is something that every first-year neuroscience graduate student learns, which is that if you were to step on a sharp object with a bare foot, you would not need to make the decision to retract your foot. You would automatically do that, provided you have a healthy nervous system. There are mechanisms in place that cause the retraction of that limb by way of ensuring that the proper muscles contract and other muscles do not contract. In fact, that they fully relax. Okay, so in the case of stepping on a sharp object, like a piece of glass or a nail or a tack, you would essentially activate the hip flexor to lift up your foot as quickly as possible. In doing so, that same neural circuit would activate a contralateral, meaning opposite side of the body circuit, to ensure that the leg, the foot that's not stepping on the sharp object, would do exactly the opposite and would extend to make sure that you don't fall over. All of that happens reflexively. It does not require any thought or decision making. However, if your life depended on walking across some sharp objects, let's say, let's make it a little less dramatic so it's not like the Die Hard movie or something where he has to run barefoot across the glass, although that's a pretty good example of what I'm describing here. But let's say you had to walk across some very hot stones to get away from something that you wanted to avoid. You could override that stretch reflex by way of a decision made with your upper motor neurons, your insula, and your cognition, and almost certainly those van Economo neurons, which would be screaming, don't do this, don't do this, don't do this, could shuttle that information to brain areas that would allow you to override the reflex and essentially push through the pain. And maybe even, in fact, even not experience the pain to the same degree or even at all. So these van Economo neurons sit at a very important junction within the brain. They pay attention to what's going on in your body, pain, pleasure, etc. And that includes what's going on with your limbs and your limb range of motion. They also are paying attention and can control the amount of activation, kind of alertness or calmness that you are able to create within your body in response to a given sensory experience. And as I mentioned before, they seem to be uniquely enriched in humans. They seem to be related to the aspects of our evolution that allow us to make decisions about what to do with our body in ways that other animals just simply can't. Now, there are a number of different types of stretching or methods of stretching. Broadly defined, we can describe these as dynamic, ballistic, static, and what's called PNF stretching. PNF stands for Proprioceptive Neuromuscular Facilitation. The first two that I mentioned, dynamic and ballistic stretching, both involve some degree of momentum and can be distinguished from static and PNF type stretching. Now, to distinguish dynamic stretching from ballistic stretching, I'd like to focus on this element of momentum. Both involve moving a limb through a given range of motion. In dynamic stretching, however, it tends to be more controlled, less use of momentum, especially towards the end range of motion. Whereas in ballistic stretching, there tends to be a bit more swinging of the limb or use of momentum. But again, dynamic and ballistic stretching both involve movement, so we have to generate some force in order to create that movement. Ballistic stretching involving a bit more momentum or sometimes a lot more momentum, especially at the end range of motion. Now, both of those are highly distinct from static stretching, which involves holding the end range of motion, so minimizing the amount of momentum that's used. Static stretching can be further subdivided into active or passive, right? There are different names for these kinds of approaches. You can hear about the Anderson approach or the Janda approach. You can look these sorts of things up online. There's also passive static stretching, in which it's more of a relaxation into a further range of motion. And that can be a subtle distinction. Nonetheless, static stretching involves both those types of elements, active and passive, but is really about eliminating momentum. And then there's the PNF, the Proprioceptive Neuromuscular Facilitation. And proprioception has several different meanings in the context of neuroscience and physiology. To just keep it really simple for today, proprioception involves both a knowledge and understanding of where our limbs are in space and relative to our body, typically relative to the midline. So the brain is often trying to figure out where are our limbs relative to our midline down the center of our body. And if your goal is to increase your hamstring flexibility and the flexibility and range of motion of other related muscle systems, you might put a strap around your ankle and pull that muscle, or I should say, that limb towards you. You're not going to pull the muscle towards you. You're going to pull that limb, your ankle towards you, to try and get it sort of back over your head, and then progressively relaxing into that, or maybe even putting some additional force to push the end range of motion and then relaxing it, and then actually trying to stretch that same limb or increase the limb range of motion without the strap. There's a huge range of PNF protocols. Those protocols can be done both by oneself, with or without straps, with machines, with actual weights, or with training partners. So specific exercises to target specific muscle groups aside, we've now established that there are four major categories of stretching, or at least those are the four major categories I'm defining today. But in terms of increasing limb range of motion in the long term, of truly becoming more flexible as opposed to transiently more flexible, static stretching, which includes PNF, appears to be the best route to go. So whether or not you want to maintain, reestablish, or gain limb range of motion, static stretching of holds of 30 seconds appear to be best. Now the question is, how long should you do that? And how many sets should you do that? And how many times a week should you do that? To answer those questions, I'm going to turn to what I think is a really spectacular review. The title of the paper is The Relation Between Stretching Typology and Stretching Duration, the Effects on Range of Motion. First of all, and I quote, all stretching typologies showed range of motion improvements over a long-term period. However, the static protocols showed significant gains with a p-value less than 0.05, which means a probability that cannot be explained by chance alone, when compared to ballistic or PNF protocols. So again, what we're hearing is that static stretching is the preferred mode for increasing limb range of motion. Although here they make the additional point that static stretching might even be superior not just to ballistic stretching, but also to PNF protocols. The authors go on to say, time spent stretching per week seems fundamental to elicit range of movement improvements when stretches are applied for at least or more than 5 minutes per week. Okay, this is critical. This is not 5 minutes per stretch. Remember, 30 seconds per static stretch, but at least 5 minutes per week. So what this means is that we should probably be doing anywhere from 2 to 4 sets of 30-second static hold stretches 5 days per week. So what would an effective stretching protocol look like? We're all trying to improve limb range of motion for different limbs and different muscle groups. Let's talk about hamstrings for the time being. This could, of course, be applied to other muscle groups. Let's say you want to improve hamstring flexibility and limb range of motion about and around the hamstring and involving the hamstring. You would want to do 3 sets of static stretching for the hamstring. You would do that by holding the stretch for 30 seconds, resting some period of time, then doing it again, holding for 30 seconds, resting some period of time, and then holding it for 30 seconds. That would be one training session for the hamstrings. I have to imagine that you'd probably want to stretch other muscle groups as well in that same session. So 3 sets of 30 seconds each, get 90 seconds, and you would do that ideally 5 times a week or maybe even more. One thing that did show up in my exploration of the peer-reviewed research is this notion of warming up for all this. We haven't talked about that yet. In general, to avoid injury, it's a good idea to raise your core body temperature a bit before doing these kinds of stretches, even these static stretches, which we can sort of ease into and don't involve ballistic movement by definition. And the basic takeaway that I was able to find was that if we are already warm from running or from weight training or from some other activity, that doing the static stretching practice at the end of that weight training or cardiovascular or other physical session would allow us to go immediately into the stretching session because we're already warm, so to speak. Otherwise, raising one's core body temperature by a bit by doing 5 to 7, maybe even 10 minutes of easy cardiovascular exercise or calisthenic movements, provided you can do those without getting injured, seems to be an ideal way to warm up the body for stretching. We should be warm or warm up to stretch, although those warm-ups don't have to be extremely extensive. And then just by way of logic, doing the static stretching after resistance training or cardiovascular training seems to be most beneficial. In fact, and unfortunately we don't have time to go into this in too much detail today, I was able to find a number of papers that make the argument that static stretching prior to cardiovascular training, and maybe even prior to resistance training, can limit our performance in running and resistance training. I realize that's a controversial area. You have those who say, no, it's immensely beneficial. You have those who say, no, it inhibits performance. And those that say, no, it's a matter of how exactly you perform that static stretching and which muscle groups and how you're doing this and how much time in between static stretching and performance. But to leave all that aside, doing static stretching after some other form of exercise, and if you, not after some form of exercise, after a brief warm-up to raise your core body temperature, definitely seems like the right way to go. I'm guessing that most people are not doing 5 days a week of dedicated static stretch, range of motion directed training. But it does appear that that frequency about the week, getting those repeated sessions, even if they are short for an individual muscle group, turns out to be important. They're going to offset the age-related losses in flexibility for sure, if one is dedicated about these practices. Some of you may be familiar with the so-called Anderson method. It's been around for a long time. Anderson has an interesting idea and principle, which is thread through a lot of his teachings, that I think are very much in keeping with the study that I'm about to describe next, where he emphasizes to stretch to the end of the range of motion, but not to focus so much on where that range of motion happens to be that day. So for instance, not thinking, oh, I can always touch my toes, for instance, and therefore that's the starting place for my flexibility training today. But rather take the entirety of your system into account each day and understand that, okay, provided you're warmed up appropriately, that you're now going to stretch your hamstrings, for instance, and you're going to reach down for your toes, but that your range of motion might be adjusted that day by way of tension and stress or by way of ambient temperature in the room, and to basically define the end range of motion as the place where you can feel the stretch in the relevant muscle groups. So what does this mean? This means feel the muscles as you stretch them. Don't just go through the motions. And this means don't get so attached to being able to always achieve, for instance, a stretch of a given distance within a given session. You might actually find that by just finding the place where you can't get much further and holding the static stretch there, that on the second and third set that you happen to be doing that day, that your range of motion will be increased considerably. Now, along these lines, there's this even more nebulous variable, this even more kind of subjective thing of how much effort to put into it. Should you push into the stretch? Would you even want to bounce a tiny bit? Would you want to reach into that endpoint and try and extend it within a given set and session? And for that reason, I was excited to find this paper entitled A Comparison of Two Stretching Modalities on Lower Limb Range of Motion Measurements in Recreational Dancers. It's a 6-week intervention program that compared low-intensity stretching, which they call micro-stretching. But to be very clear, micro-stretching in the case of this manuscript is low-intensity stretching, and they compared that with moderate-intensity static stretching on an active and passive ranges of motion. Basically, what they found was that a 6-week training program using very low intensity stretching had a greater positive effect on lower limb range of motion than did moderate intensity static stretching. Here I'm quoting them. The most interesting aspect of the study was the greater increase in active range of motion compared to passive range of motion by the microstretching group. So this relates to what we were just talking about a few moments ago as it relates to the Anderson method, which is that very low intensity stretching, meaning effort that feels not painful, and in fact might even feel easy or at least not straining to exceed a given range of motion, turns out to not just be as effective, but more effective than moderate intensity stretching. So what is low intensity static stretching? Well, they define this as the stretches were completed at an intensity of 30 to 40%, where 100% equals the point of pain. Right? So 30 to 40% in these individuals, and again, I'm paraphrasing, induced a relaxed state within the individual and the specific muscle. And here they were holding these static stretches, I should mention, for 1 minute, not 30 seconds. Now, the control group was doing the exact same overall protocol, so daily stretching for 6 weeks, the same exercises, holding each set for 60 seconds, but we're using an intensity of stretch of 80%, where again, 100 represents the point of pain, the point where the person would want to stop stretching. I find these data incredibly interesting for, I think, what ought to be obvious reasons. If you're going to embark on a flexibility and stretching training program, you don't need to push to the point of pain. In fact, it seems that even just approaching the point of pain is going to be less effective than operating at this 30 to 40% of intensity prior to reaching that pain threshold, the pain threshold being 100%. Now, of course, this is pretty subjective, but I think all of us should be able to register within ourselves as to whether a given range of motion or extending a given range of motion brings us to that threshold of pain or near pain. And according to this study, at least, operating or performing stretching at an intensity that's quite low, that's very relaxing, turns out to be more beneficial in increasing range of motion than is doing exercises aimed at increasing range of motion at a higher intensity. Okay, so lower intensity stretching, I should say lower intensity static stretching, appears to be the most beneficial way to approach stretching. And I think that's a relief probably to many of us, because it also suggests that the injury risk is going to be lower than if one were pushing into the pain zone, so to speak. I want to just briefly return to this idea of whether or not to do ballistic or static stretching before some sort of skill training or weight training, any kind of sport or even cardiovascular exercise like running. There are instances, for example, where an individual might want to do some static stretching to increase limb range of motion prior to doing weight training, even if it's going to inhibit that person's ability to lift as much weight. Why would you want to do that? Well, for instance, if somebody has a tightness or a limitation in their neuromuscular connective tissue system, someplace in their body and system that prevents them from using proper form that they can overcome by doing some static stretching, well, that would be a great idea. There are instances where people are trying to overcome injuries, where they're trying to come back from a reparative surgery or something of that sort, coming back from a layoff, where some additional static stretching prior to cardiovascular weight training or skill training or sport of some kind is going to be useful, because it's going to put us in a position of greater safety and confidence and performance overall, even if it's adjusting down our speed or the total amount of loads that we use. And similarly, there are a lot of data pointing to the fact that doing some dynamic or even ballistic stretching prior to skill training or cardiovascular weight training can be beneficial, in part to warm up the relevant neural circuits, joints, and connective tissue and muscles, and as well to perhaps improve range of motion or ability to perform those movements more accurately, with more stability, and therefore with more confidence. Thus far, we've been talking about stretching for sake of increasing limb flexibility and range of motion, but there are other reasons, perhaps, to embark on a stretching protocol that include both our ability to relax and access deep relaxation quickly. I'd like to return to this idea and this place, this real estate within our brain that we call the insular cortex, the insula. As you recall, way back at the beginning of this episode, we were talking about the von Economo neurons that Konstantin von Economo, the Austrian scientist, discovered. And the fact that we are able to make and perform interpretations of our internal landscape, pain, our dedication to a practice. For instance, whether or not we are in pain because it's a practice that we are doing intentionally and want to improve ourselves, or whether or not it's pain that's arriving through some externally imposed demands or situations. The insula is handling all that. And fortunately, there's a wonderful paper that was published a few years ago now in the journal Cerebral Cortex, entitled Insular Cortex Mediates Increased Pain Tolerance in Yoga Practitioners. This study explored the effects on brain structure volume in yoga practitioners. And for those of you out there that are aficionados in yoga, they pulled subjects from having backgrounds in here I'm probably going to mispronounce these different things, and forgive me, the Vinyasa yogas, the Ashtanga yogas, Iyengar yogas, the Sananda yogas. Okay, so some people were new to these practices, some were experienced. The important takeaways were that they took these yoga practitioners and they didn't explore their brain structure in the context of yoga itself. They looked at things like pain tolerance. So they used thermal stimulation. Basically, they put people into conditions where they gave them very hot or very cold stimuli and compared those yoga practitioners of varying levels of yoga experience to those that had no experience with yoga, so-called controls. And they found some really interesting things. There are a lot of data in this paper, but here's something I'd like to highlight. The pain tolerance of yoga practitioners was double or more to that of non-yoga practitioners. They also found significant increases in insular, again, the insula, this brain region, gray matter volume. Typically, when we talk about gray matter, we're talking about the so-called cell bodies, the location in neurons where the genome is housed and where the kind of all the housekeeping stuff is there. And then white matter volume tends to be the axons, the wires, because they're ensheathed with this stuff that appears white in MRIs and indeed is white under the microscope and indeed is white. It's actually lipid, which is myelin. So increased gray matter volume of the insula is a significant finding because what it suggests is that people that are doing yoga have an increased volume of these areas of the brain that are associated with interoceptive awareness and for being able to make judgments about pain and why one is experiencing pain, not just to lean away from pain, but to utilize or leverage or even overcome pain. And I find this interesting because there are a lot of activities out there that don't create these kind of changes in brain volume, especially within the insula. So it appears that it's not just the performance of the yogic movements, but the overcoming or the kind of pushing into the end ranges of motion and to push through discomfort to some extent. Of course, we want people doing that in a healthy, safe way, but that allows yoga practitioners to build up the structure and function of these brain areas that allow them to cope with pain better than other individuals and to cope with other kinds of interoceptive challenges, if you will, not just pain, but cold, not just pain, but discomfort of being in a particular position to do that. And again, we wouldn't want people placing themselves into a compromised position, literally, that would harm them, especially given that earlier we heard that micro-stretching of the kind of non-painful sort, low-intensity sort, is actually going to be more effective for increasing end range of motion. But this study really emphasizes the extent to which practitioners of yoga don't just learn movements, they learn how to control their nervous system in ways that really reshapes their relationship to pain, to flexibility, and to the kinds of things that the neuromuscular system was designed to do. So if ever there was a practice that one could embark on that would not only increase flexibility and limb range of motion, but would also allow one to cultivate some improved mental functioning as it relates to pain tolerance and other features of stress management that no doubt wick out into other areas of life, it appears that yoga is a quite useful practice. But of course, yoga isn't the only way to increase limb range of motion and flexibility. Up until now, we've described a number of different ways to do that, and we've arrived at some general themes and protocols. Again, we can revisit a couple of them now just in summary and synthesis. Static stretching appears to be at least among the more useful forms of stretching. It really does appear that getting at least 5 minutes per week total of stretching for a given muscle group is important for creating meaningful, lasting changes in limb range of motion. And that is best achieved by 5-day-a-week or 6-day-a-week or even 7-day-a-week protocols. But those can be very short protocols limited to, say, 3 sets of 30, maybe even 45 or 60 seconds of static hold, although 30 seconds seems to be a key threshold there that can get you maximum benefit. And of course, to always warm up or to arrive at the stretching session warm. Thank you once again for joining me today for a discussion about the neural and neuromuscular and connective tissue and skeletal aspects of flexibility and stretching. And as always, thank you for your interest in science.